All right, so this is the problem we're talking about, right?
Yeah.
Okay, so I have this mass here, the 2 kilogram mass that's sitting on the table. Maybe I don't know if I'll make this bigger. This will help. Go full screen with this. Wow. All right, hopefully that's good. It's strange that the picture's all the way over here on this side, but there's these 2 masses, they're connected by a spring. Here's 2 kilograms, it sits on the surface, and here's 1 kilogram, and it is hanging from this string. And so what we're trying to do is find what is the upper block's acceleration. If the coefficient of friction between the blocks in this case is 0.3, it may randomize. No, it seems to be the same for everyone, but sometimes these things are randomized. Here's the thing. It's asking what is the well, I'm sorry, before I go off and talk about this thing too much, do you have a specific question about this, or is it all just crazy?
Yeah, it's mainly just like how to do the whole thing.
Okay, so it's asking what is the acceleration of this block, but there's two things that I want to realize that make this different than a regular Newton's second law problem, and they're this. If the block that's sitting on the table moves a little bit to the right, then the block that's hanging goes down exactly the same amount, which means in the same amount of time, their displacements are the same, which means that their velocities are the same, which means that their accelerations are the same. So a useful thing to remember or realize about this problem is that the accelerations of both blocks are the same. There's not 2 different accelerations. There's 2 different blocks, but not 2 different accelerations. The second thing is that the tension force that pulls the block that's on the horizontal, that tension force that pulls to the right, is the same tension force that, I just realized I've done this. I can't see the waiting room, and if anybody else comes in, I won't be able to see them. There we go. And nobody's else trying to get in, so that's nice. Okay. So that tension that pulls upward on this string that's hanging, it's the same tension. Now, just recently, I made a video about this one, and in that video, I made free body diagrams. Luckily, I have that right here. Boy, this is going so well. You can all see this, my free body diagrams and whatnot?
Mm-hmm. Yeah.
Okay. So here's the diagram itself. Gosh, I look like I'm such a pro at this. First time. So here I've drawn a free body diagram for this block that sits on top. I call it M1. It's got its weight downward. It's M1G that I put there, normal force upward, tension to the right, and friction force to the left. Those are the forces that affect its motion. Now, I'm hoping at this point that clever students are looking at this free body diagram and realizing, without ever writing Newton's second law, that the normal force that points upward is equal to the weight force that points downward. They have to be. Otherwise, this block would fly up into the air or sink down into the ground. And so I've just written here that the normal force is equal to M1 times G. What I'm going to do then to solve the problem is I'll write the sum of the forces that act horizontally on the block. So I have the tension that points to the right and the friction force that points to the left. That's equal to M1 times A. It's really important that I put that M1 there, that I realize that it's M1 that describes the motion of this object, because my algebra will get all fouled up if I don't keep it clear which mass I'm putting in which place. A lot of times, well, I'll encounter students who are careless about it and just, well, I'll put whatever mass and see if I can get the right answer. But since I'm talking about object 1 here, I should be using the mass of object 1. In the very last step that I do here, I realize that the friction force is equal to the coefficient of friction times the normal force. So right below here, I put the coefficient of friction multiplied by the normal force, which is M1G. I realized up here that the normal force was equal to M1G. And so now I have this complete and ugly equation for the motion of the block that sits on top. The tension minus mu M1G is equal to M1A. Perfect. Except I can't solve for the acceleration on top of the block, of the block that's on top, because I know it's mass, I know G, I know it's mass, I know mu, but I don't know the tension. The whole deal with this type of problem, and really the learning, the reason why we do this, is that I don't know what the tension is, and I don't know what the acceleration is. I'm going to have to find it. So I need a second equation. And I get the second equation by drawing my free body diagram for the mass that's hanging. The weight of M2G hanging downward, the tension upward, which is the exact same tension as this tension over here. They're the same because according to Newton's third law, they're an action-reaction pair. So the two tensions are equal to each other. So I write the Newton's second law, the sum of the forces. Here's another little bit of a quirk here with solving this kind of problem in a way that students go wrong. I have to choose downward to be the positive direction. I have to choose downward to be the positive direction, because M1 is going to move to the right and M2 is going to move downward. So I want to choose the positive direction so that it's the same direction of motion. I know that the magnitudes of the accelerations are the same, but I have to ensure that the direction of the accelerations are going to be the same. If you make this one little mistake, problem's over, can't solve. It goes badly. But I'm going to be smart. I'll choose downward to be the positive direction. M2G minus the tension is equal to M2A. Now, I said that they have the same acceleration. Am I going to use this equation to find the acceleration? Well, that'd be great, except I don't know the tension. So I have two equations, an equation over here on the left where I don't know the tension, I don't know the acceleration, and an equation over here on the right where I don't know the tension, I don't know the acceleration. But if I have two equations with two unknowns, I can solve it algebraically. Now, that relies on your algebra skill. Is that intimidating, doing the algebra to solve for that? No. Because you know what's going to happen. If you say that it is, I'm just going to do it.
Don't you just set them equal to each other?
Well, what I could do, a way that I could do it, depends on maybe how your math teacher trained you to do it. But a way that I could do it is I could solve the equation on the left for the tension, solve the equation on the right for the tension, and set them equal to each other, and then solve for the acceleration.
Mm-hmm.
I could do that. You want to see me do it? I'm happy to do it.
Yes, please.
Okay, so the reason why I was saying that I'm happy to do it is because I have this fancy gizmo here. I have an art tablet that I never get to use. And I'm excited to do some algebra live for folks and see what happens. A little bit of a warning in advance. This is probably going to be ugly, so be a little bit forgiving if you can be. So there's my pointer. So here I go. I have an equation that says that the tension minus mu M1 times G is equal to M1 times A. Hey, that's not so bad. I'm going to solve that equation for the tension. And the way that I'll do that simply is just add mu M1G to the other side of the equation. So it's M1A plus mu M1G. Hey, not so bad. I thought that if I did this under pressure, I would freak out and it would go horribly, but it's actually going okay. What was the other equation? The other equation was M2G minus the tension is equal to M2 times A. Now, what I would do, my style of doing algebra, is I would just take this T here and plug it in where that T is. But that sometimes folks find that a little bit confusing because I would have to make this negative and I would have to make this negative. So let's do what I originally said that I was going to do. I'm going to solve this equation for T. The way that I'll do that is add T to this side and subtract M2A from this side. So I have that T is equal to M2G minus M2A. So I have this equation that says that T is equal to this. And I have this equation that says that T is equal to this. And in order to solve it, I'll set the two equations equal to each other so that M1 times A plus mu M1 times G, which is my first equation, is equal to M2 times G minus M2 times A. And so what I've done is I've eliminated the tension from the equations. The tension is gone. And now I can just solve for the acceleration. Well, it's the same rules of algebra as always. I want to get my variable by itself on one side of the equation. I have an m1a over here and an m2a over here. I want to get them together. So I'll add this m2a over to this side of the equation. At the same time, I'll take this mu m1g and subtract it to the other side of the equation. So that m1a plus m2a is equal to m2g minus mu, oops, my m1's small. That's the first, it really does look like hell, but that's the first real mistake that I feel like, mu m1g. I want to get the acceleration here on the left-hand side, so I'll factor out the acceleration so that a, m1 plus m2 is equal to, here I'll factor out the g just for fun, m2 minus mu m1 times g. Now, divide both sides, and this is going to look ugly because I'm running out of space here, but divide both sides by m1 plus m2, and my final result is that m2 minus mu m1 divided by m1 plus m2 multiplied by g is equal to a. And that is the final answer for the acceleration. If the problem were to also ask me to find the tension, which I don't know if it does or not, but once I have this acceleration, I could go back to either one of these equations and find the tension.
Mm-hmm.
How about that?
Yeah.
Does everybody have that down?
Yeah, I got that.
Sarah's here, but she's not talking to us today.
I'm just trying to follow along.
Okay. How's that going for you?
I'm understanding parts of it, but yeah.
If you think that the physics that you're doing is hard, you're right. Because I'm not trying to hide anything from you. This is real deal physics. If you take your university physics class, this is the kind of stuff that's going to happen. So, you know, I'm kind of a believer in doing challenging things. I do that for myself, and so I do that for my students by providing you with problems that are difficult to solve. And I know when I assign homework 16, that the people who try to do homework 16 are going to find it to be rough and challenging to do. And that doesn't bother me too much. So I'm happy to solve it for you here and show you what the acceleration is equal to. So you calculate that and you get the number. But it's also important that you get the idea. I have two objects, which allows me to write Newton's second law twice, because there are two unknowns. And then I use my algebra skill to find out what that acceleration is in the end. How about that? I'm going to go ahead and delete this so that I can use my board again. Ooh, that was squeaky. So I gotta figure out how to delete. Oh, there we go. Oh, excellent. Good. So that was a bad idea right there. Go away. Okay. So that was Caitlin's question. Gabby, do you have a question? We sort of round robin this. So I put you on the spot all of a sudden, but.
I'm just gonna go to, I have to go to.
By the way, if you want to go through, if anybody wants to, this is not a demand, just a suggestion. If anybody wants to go through assessment 3 prep, then we can do that as well. Before we had our closure, we did assessment 2 prep, and that didn't go super well for a lot of folks. But this time, you'll be doing it at home in your pajamas with lots of time to do it, and actually no way for me to stop you from using the internet or your notes or your mastering or whatever in order to work those out. So I'm hoping that assessment 3 is going to go a lot better than assessment 2 did. But I guess we're going to find out tomorrow. Today's Thursday, right? Lose track of the date of the week.
Well, I already started it, but some of the ones in the beginning I was confused with. Like,
On the prep?
yeah, like the true or false ones. Like,
Still using my art pen as a pointer. Wow, it's a lot of questions. Okay. Is everybody cool with just going through and looking at these, or?
Yeah.
All right. Nobody expected that there was going to be a monster crowd here. So with just the four of us, it's pretty easy to just sort of speak up. And I think I should do this in standard view. Oh, there we go. So should I just rock right through these and you guys chime in with any questions that you have?
Yeah.
yeah.
Okay. Oh my gosh, awkward as hell. And there's no difference. There's no difference here if you're sitting in the classroom and I'm standing in the front and I'm answering the questions, but for some reason, seems to be awkward. So a collision between an SUV and a small hybrid car, the SUV exerts a larger force on the hybrid than the hybrid exerts on the SUV. No, that is false. And the reason why I'm so quick to say false, my art pen has buttons on it. Not the solution view. I don't want to see the solution. No, 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 I don't want to see it. I already know the answer. Come on now. The answer is false. And the reason why I know immediately is because Newton's third law says action, reaction. When one object exerts a force on the other, the forces are equal and opposite. But then what happens, and you heard me complain about this, that we say a thing that's a law of the universe, and then the students say, yeah, Charlie, but this one's a duck. This is different because it's a different situation. No. When two objects interact, no matter what they are, if they're an SUV and a car, if they're an asteroid and a planet, if they're a galaxy and another galaxy, action, reaction is the law of the universe. Now, you might say, well, the SUV is very large and the car is very small. So surely the SUV exerts a larger force, but it doesn't. What happens is, because the SUV has a larger mass and the car has a smaller mass, the car will have a larger acceleration and the SUV will have a smaller acceleration. So if this collision happens and you're riding in the SUV, you feel a small acceleration. And if you're in the hybrid, you go flying and large acceleration. So the accelerations are different, sure, but the forces are the same always. And this question is designed to trick you into second guessing that idea that the forces are always equal and opposite. Do we get that?
Yeah, that question, that's exactly what I did. So
Okay.
now I get it.
Box is placed on a table which rests on the floor. The box pushes on the table. The reaction force to the box's push on the table is the table's push on the floor. No, that is false. Action-reaction pairs are one force acting on another. One thing pushes on another. Not only that, the nature of the force has to be the same. So when a box is placed on a table, the box pushes downward on the table and the table pushes upward on the box. That's the action-reaction pair. And they're both normal forces. They're both forces of contact. The box force pushing down and the table force pushing up. Good?
Mm-hmm.
Yeah, good. But why would I just pushed next? Oh, because I didn't submit it. I got to get my credit. You're so right, Charlotte. Well, thank you. I knew that I was. In order to get an object moving, you must push harder on it than it pushes back on you. That is not true, because according to Newton's third law, action, reaction, you exert a force on an object, that object exerts an equal and opposite force back on you. Action, reaction. Once again, a question trying to get you to second guess an idea of physics. The rockets in a spaceship in outer space far from gravity suddenly lose power and go off. The spaceship will gradually slow to a stop. Boy, these are all false as false can be. Newton's first law, the law of inertia, that it's the natural tendency of objects to persevere in their motions, to continue on forever and ever and never stop. So when you shut the rocket engines off in space, the spaceship keeps going. In fact, this is what we do. For example, we launch an Apollo mission at the moon. The rockets, we use a rocket to get the spacecraft off the surface of the Earth and get it into space. We use a rocket to get the spacecraft going in the right direction. But the spacecraft spends 4 days just cruising through space. No rockets, no engines, no power of any kind except to, keep the astronauts warm and whatnot. Because once you get going, you keep going. The reason why gradually slow to a stop is appealing as an answer here is because here on the surface of the Earth, there's viscous drag, there's friction, there's all of these things that can cause an object to slow to a stop. But in space, there's no such thing. And so the thing just keeps on going forever and ever. Okay?
Mm-hmm.
You're in a, you know what? I'm going to get my credit because I'm going to get 100 on this. You got to answer. That's false. Submit. There we go. Green check marks are so satisfying when you're doing that. You're in a train traveling on a horizontal track and notice a piece of luggage starts to slide directly toward the front of the train. From this observation, you can conclude that the train is slowing down. And I think we've all sort of had this experience in everyday life. So my hope would be that everybody would get this question right. The suitcase has inertia. And once the suitcase gets going, it wants to keep going. When the train begins to stop, the suitcase keeps going. And so the train, the suitcase goes toward the front of the train according to Newton's first law, the law of inertia. Yeah?
Mm-hmm.
Great. We're doing great. An elevator suspended by a cable is moving downward, but it's slowing down. The tension in the cable must be, so it's heading downward. The tension force is upward. The weight force is directed downward. In order to slow down, the tension force upward has to be greater than the weight of the elevator so that the net force is upward so that the acceleration decreases the velocity of the elevator. In order to stop the elevator, you have to pull harder upward on the elevator than the weight force pulls downward. So that's correct. Crate sliding down an inclined ramp, speed of 0.55 meters per second. At constant speed, here's the thing, you have to watch out for this in physics questions because constant speed means zero acceleration. And that changes the character of a problem very often. So it's going down at a constant speed, so the sum of all forces must be equal to zero. If the acceleration is equal, perpendicular, vertical, up the ramp, down the ramp, zero. None of the forces. So Newton's second law says that the sum of all forces is equal to the mass times the acceleration. If the acceleration is zero, then the sum of all forces is zero. If the sum of all forces is zero, it doesn't point in any particular direction. Correct. You guys yell at me if I'm going too fast.
You're good.
Bucket is being lowered by a light rope with constant downward velocity. This is different than the elevator. The elevator was being lowered on its cable but slowing down. This is going down at constant speed. If it's going down at constant speed, that means the acceleration is equal to zero. That means that the net force must be equal to zero. That means that the tension in the rope upward must be equal to the weight downward. Get that? Those forces are equal, so the acceleration is zero. Where people go wrong with this is sometimes they think that if the total force is zero, the thing's not moving. because that happens often. If I set my coffee mug here and it sits on my desk and it's not moving, the sum of the forces is equal to 0. But that sum of the forces equal to 0 means the acceleration is 0. Doesn't mean the velocity is 0. So this bucket's moving with constant velocity, no acceleration, and therefore the forces add up to 0, and therefore the tension force upward is equal to the weight force downward. Get my points correct. An object is moving with a constant non-zero velocity. Which of the following statements about it must be true? It's moving with a constant non-zero velocity. Constant velocity means its acceleration is 0. If the acceleration is equal to 0, then the net force is equal to 0, and I see that that answer appears right here. Right. So it still feels to me that a lot of physics questions are always trying to get you to second guess the thing that you know. The laws of physics are really quite simple, so you have to learn to apply them very, very strictly to get past all this gobbledygook of answers that sort of sound appealing but are actually wrong.
Yeah.
Person weighs 700 newtons, is riding on an elevator moving upward but slowing down. This person's going to feel lighter. So that scale is going to read less than 700 newtons. And the reason why I know that that's going to be the correct answer is because I've been on an elevator. And I know when I'm going upward on an elevator and the elevator slows down, I feel a little light as the elevator comes to a stop. So why should this be so from a physics point of view? Well, if I draw a free body diagram for a person standing on an elevator, which I did in one of the lectures, if I draw that free body diagram for a person standing on an elevator, the normal force is upward, the weight force is downward. When I'm slowing, the normal force upward has to be less than the weight, so that the net force is downward, so that the upward motion is forced to a stop. The normal force is really what you feel. The normal force is your apparent weight. The normal force is what the bathroom scale reads. So when you're slowing down in an elevator, you feel light, and the scale reads that you are light because the normal force is less. You actually weigh the same. The force of gravity on you is your weight, and the motion of the elevator doesn't change your weight. That's sort of a tricky one, but I talked about solving that problem in detail in one of the lectures. I don't know which one. Probably applied Newton's applications of Newton's second law. We okay with that?
Mm-hmm.
Tricky one, I think. What is the mass of an object that experiences gravitational force of 685 newtons near the surface of the Earth? Well, all I have to do is divide by 9.8. What's 685 divided by 9.8? Oh, this is where I'm going to get it wrong. I should be doing this in my head. You can't see my calculator right here.
69.
Yeah, 69.89. So I'm going to select that and submit and be right, because the weight of a thing is m times g. So W is equal to m times g. I guess maybe we're moving into a part of this prep where it's going to start being calculations. What is the magnitude of a net force required to accelerate a car from 0 to 27 meters per second in 10 seconds? Well, in order to know the force, I need mass times acceleration, F equals ma. But I don't know the acceleration, but they give me this 27 meters per second.
Do you just calculate the acceleration by doing change in velocity over change?
That's right. So it's going to be 27 divided by 10, which I don't need my calculator for, is 2.7. Because it's 27 minus 0, which is 27, divided by 10 is 2.7. Multiplied by 1,200 is 3,240. F equals ma. Very simple. Very, very simple. Oh, this thing. I keep forgetting to remove this from this assignment. It drives me nuts. Look how they've named these forces here. Shown in the figure, a woman is straining to lift a large crate. Well, that's sexist. But without success, because it's just too heavy. We denote the forces on the crate as follows. P is the upward force being exerted on the crate by the person. C is the contact force. So C is actually the normal force in this case. and W is the weight of the crate. How are the magnitudes of these forces related while the person is trying unsuccessfully to lift the crate? Well, the acceleration of the crate is equal to 0 because it's not successfully lifting it. So the acceleration is 0. That means the forces that act upward are equal to the forces that act downward. This, I feel, is a confusing question because all of a sudden there's these greater than or less than signs. And I want to point out that Newton's second law doesn't say the sum of the forces is greater than ma. It doesn't say the sum of the forces is less than ma. It says the sum of the forces is equal to ma. You say, but Charlie, this is an old lady lifting a crate. I assume that she's old because that's not a very young hairstyle. But and she has one shoe on here. Do you see? You can tell there's like the top of the shoe, no shoe on the other foot.
Is that her toe? On that other, what is that other foot?
I don't know, but there's nothing going across the ankle here. She's got one shoe on, okay? Crazy lady lifting a crate. Doesn't matter, crazy lady lifting. I only had one coffee. That's the problem. Sum of the forces is equal to the mass times the acceleration. So this has to be an equality. So these last two answers are the only ones that are relevant. And her pull force P is upward. The contact force, which is the normal force, is upward. And the weight is downward. So P plus C is equal to W. I honestly always think that I want to pull that question out of this assignment because I don't think it helps anyone learn if you just change the names of things. Because physical laws aren't based on the names of things. It doesn't matter. As a matter of fact, here I go. You probably remember Richard Feynman's a famous physicist, and he recalls this story about when he was a kid. And he would go on walks with his father, and he would ask his father, what kind of bird is that? What kind of bird is that? And his father would tell him the names of the birds. And he thought his father was really clever, like knew all the bird names. And he found out later in life that his father was making up the names of the birds. He was just making names up. And so he said to him, he said, wait, all those names were fake, you told me. And he said, well, it's because the name doesn't matter. What matters is behavior. What matters is the description of the nature of a thing. And the names don't matter. And this problem kind of pretends like how you name things matters. And it doesn't. Or maybe it's supposed to teach you to realize that it doesn't matter what you call it. I don't know. I don't like it. She got one shoe on. It's freaking me out. Look at this force. This force here, I'm not even reading the question. This force here is down at an angle. And I know from being in physics class that when a force is down at an angle, I have to do something about that. I have to find the components. In the same way as when I did a projectile motion problem, a projectile was launched at an angle, I have to find the components of that force. So here's the angle. Here's the push force P. And here's the angle. So the horizontal force, which points to the left here, would be P cosine theta. And the vertical force that points downward would be P sine theta. So I'm probably looking for an answer that has components in it. I better read the question first. A push force of magnitude P acts on a box of weight W shown in the figure. The push is directed at an angle theta below the horizontal. The box remains at rest, which means the acceleration is equal to 0, which means the push force to the left is opposed by the friction to the right. The friction force on the box due to the floor is equal to P cosine theta. I'm pushing the box to the left with a force P cosine theta, and it's not moving. So there must be a force that points in the opposite direction that is equal to the force that I'm pushing, that is making the total force equal to 0, so that the acceleration is equal to 0. That force would have to be equal to the force with which I push, which is P cosine theta. Submit. Green check mark. There you go.
Problems where you have to find the other component where it's like sine theta, because usually with acceleration it would be the cosine.
Yeah, that happens a lot, and sometimes when they write problems, they try to trick you up by putting the angle in a weird spot so that the sine and cosine work out different than they usually do.
Mm-hmm.
But you just have to, and that's why I say that finding the components is always about finding out which side is adjacent. And in this case, there's P, and the one side that is adjacent to the angle is the horizontal one, and that's why that's P cosine theta.
Okay.
Oh, look at this. This is just like the one that we just solved. Boxes are connected to each other by a string in the figure. The 10 Newton box slides without friction. There's no friction in this case. The pulley is ideal and the string has negligible mass. What is true about the tension T in the string? Ooh. We actually have to solve this. But I'm just trying to reason it out. So this 30 Newton weight is going to accelerate downward, which means the tension force has to be less than 30 Newtons.
So it's a negative acceleration.
Unless I choose that direction to be positive. We have a little bit more flexibility here with how we choose our coordinate system. If I choose downward to be positive, then it would be a positive acceleration. But here's the thing about my answer that I just put in here. I'm saying that T has to be less than 30, and that's true. But 20 is less than 30. 10 is less than 30. Right?
Yeah.
So I know that it's not T is equal to 30, because if T was equal to 30, then this thing wouldn't fall. Its weight downward and the tension upward would be the same, and it wouldn't fall. And I know T can't be greater than 30, because if the tension were greater than 30, then the tension upward would cause this thing to rise. So I know that it's one of the first three answers. And the middle answer, T is less than 30, is true for the two above and below, which means that's not the answer. It's got to be T is equal to 20 or T is equal to 10. I want to answer the question without solving the thing entirely. So let me guess that T is 20. I'm just going to guess that T is 20. If T is equal to 20, then the force on the 10 Newtons is 10, or is the force on the 10 Newton. See, this thing weighs 10 Newtons, which means its mass is about 1 kilogram approximately. So it's a 20 Newton force on 1 kilogram is 20 meters per second squared acceleration. On the hanging mass, if it's 20 Newtons up and 30 Newtons down, then the net force is 10 Newtons on a 3 kilogram object is 30 meters per second squared. And so if I choose this one, they don't have the same acceleration, and they must. That means by process of elimination that I know that this is the correct answer. Let me just check to verify that. If I make the tension 10 Newtons, then this is 10 Newtons on a 1 kilogram mass is going to give me 10 meters per second squared of acceleration. On the hanging mass, if it's 10 Newtons of force upward and 30 downward, then that's 20 Newtons of force acting on a 3 kilogram mass. What am I doing?
I had the answer as T is less than 30.
And it says it's correct?
Yeah.
It's weird. So it's not 20, it's not 10, but it is less than 30. What a strange question. It's not 20. Huh. Okay. I guess I'm going to be satisfied with that. Submit. It's correct. I wanted to try to reason it out with solving it. And notice I picked the right answer right off the bat. But it bothered me that, I mean.
It's kind of weird that they put, or
yeah.
I don't. Yeah.
But it can't be 20 and it can't be 10. My inclination right now, but we don't have time for it, is to actually solve the problem and find out what the tension is. But if I was doing this on a multiple choice exam, I wouldn't have time to do that. So I would have to reason it out the way that I just did. Maybe if more people complain about it, I'll post a solution to it. You know what? I'm just going to post a solution to it. So look for that on Google Classroom. I'll work out the solution to this thing in detail, and it'll show why. We just we want to make sure we use our time effectively, and I want to get through all of these. 200 Newton sled of slides. What? A 200 Newton sled of slides? A 200 Newton sled slides, the word of, okay. A 200 Newton sled slides down a frictionless hillside that rises 37 degrees above the horizontal. What is the magnitude of the force that the hill exerts on the sled parallel to the surface of the hill? 0. Boy, I answered that awfully quick. If I draw my standard free body diagram for an object on an incline, I've got a component of the weight down the incline. I've got a component of the weight perpendicular to the incline. Maybe I have a friction force that's parallel to the incline, and I have the normal force, which is the force that of contact between the incline and the object. That normal force is perpendicular to the incline. That's what the word normal means. It means perpendicular. So when it asks me, what is the magnitude of the force that the hill exerts on the sled parallel to the surface, the answer is immediately 0, because the force that the hill exerts on the sled is completely perpendicular to the hill. Some people call that a trick question. Mass M at rest on a rough inclined ramp makes an angle theta with the horizontal. What must be true of the force F on the block due to the ramp? That is the normal force. The force on the block due to the ramp is the normal force. And from my experience solving inclined plane problems, the normal force in an inclined plane problem is mg times the cosine of theta. I recommend too for assessment 3 that you make sure you know how the inclined plane free body diagram looks and the Newton's second law equations for both directions for that, because that's on assessment 3. But of course, you won't be sitting in a classroom with no notes to look at or anything like that, so you'll be able to look in your notebook and probably immediately figure that out. Assessment number 3 is going to be hard for, believe it or not, is going to be a bit hard for the cheaters, because the people who have good notes and are organized and know what they're talking about, they're going to know how to pick out the answers to the questions very quickly, whereas the cheaters are going to have to do all kinds of Google research and nonsense and whatnot. But it's okay, because sins have a way of finding punishments. 400 kilogram box lifted vertically upward at a constant velocity by 2 cables pulling at 40 degrees on either side. What is the tension in each cable? Boy, this one needs a diagram. I'm just going to really quick bring up my diagram doohickey here. So I have, wrong color, hang on. So I have this, fill tool, that's no good. You know what? Sorry, that was a terrible error on my part. So here's the crate, and there's a force that goes this way at 40 degrees. Oh, shouldn't have written that in. So there's an angle in here. I'll just call it theta because I can't write 40 in there, and it's 40 degrees. And there's another force that goes off this way. I hate this diagram, the fire of 1,000 suns. And this is also 40 degrees, same angle. And they want to know what's the tension in each. The weight, mg, is directed downward. So here's the thing. These two forces that are going up at 40 degrees, they have components that go horizontal like this. Those horizontal components don't matter at all. Those horizontal components cancel each other out. What we want is the vertical components. So there's a tension over here and there's a tension over here. They're the same tension. The whole thing's symmetric, the same tension, but they're both directed upward. T cosine theta, T cosine theta. So if I were to write this as an equation, what I need is 2 times T cosine theta, because I have 2 T cosine thetas pointing upward, has to be equal to the weight downward. In order to support the weight, I need 2 T cosine thetas directed upward to support that. So the tension is going to be M times G divided by 2 times the cosine of theta. So mg 400 times 9.8 is 3,920. There's 3,920, hasn't been divided by the cosine of theta yet. I'll divide that by 2. And they didn't give me that answer. And I have to divide by the cosine of 40 degrees. Divided by, I hope this thing's in the right mode, 40 cosine equals 2,560. Yay. Did everybody like that?
So the normal force is always cosine theta.
Well, here's the thing. Let me go back to my diagram. There is no normal force here. This block is just hanging from these chords. So there's no surfaces in contact. And so there's no normal force. But these tensions here, the reason why I chose cosine is that I wanted the component that pointed upward. The component that points upward is adjacent to the angle, and that's why I chose cosine.
Okay.
Right? I'm choosing cosine based on the context that I'm looking at. So there is no, you can't say, oh, it's always cosine. You're going to get burned on that because someone's going to make this same problem, but they're going to draw the angle down here. And when they draw the angle down here, that angle is going to produce sine instead of cosine in the answer. 3 kilogram mass, 5 kilogram mass hang vertically opposite ends of a rope that goes over an ideal pulley. If the masses are gently released from rest, how long does it take the 3 kilogram mass to rise by 1 meter? This is actually a significant calculation that you have to do in order to get the answer to this, because this is what's called the Atwoods machine. And I realized that I did not, explicitly solve the Atwoods machine in my previous lecture, and we don't have enough time if we're going to complete all of this. So I will also post, I have to remember the things that I need to post. I will also post to Google Classroom a solution of the Atwoods machine, but I'll sort of just sketch it a little bit here at first. What's my color? White. No, I'm set. Select black. Okay. The idea is this. I keep forgetting to turn the bucket off. Okay, fine. We're going to make it pretty. We're going to go with this. I can still see the stuff that I wrote. All right. You're okay, Shannon. Thanks. I appreciate it. So there's a pulley here, and you've got a mass on this side. Say it's mass 1. You've got a mass on this side. It's called mass 2. This is what's known as an Atwoods machine. And when I write the sum of the force equations for the Atwoods machine and solve them simultaneously, the result I get is this, that the acceleration is equal to m, I'm assuming m1 is the more massive, m1 minus m2 divided by m1 plus m2 multiplied by g. How did I know that? Well, I've been doing physics all my life, so I know what that solution is. I'm going to post that solution to Google Classroom. At any rate, what I have to do for this multiple choice question is I have to calculate that acceleration. m1 minus m2 over m1 plus m2 times g. I have to calculate the acceleration. And then I have to use a kinematics equation to work out what the answer is. So I'm going to have to take the difference of the masses. I don't have time for these things. I'm going to have to got my TI calculator out, ready to rock. The difference between the masses is 2 divided by 8. Because the sum of the masses is 8. That's 1/4 multiplied by 9.8 meters per second squared is 2.45 meters per second squared is the acceleration. So how long does it take the mass to rise by 0.1 meters? So that's a time. So it's going to be, according to kinematics, 2 times 1 is 2 divided by, what did I just say the acceleration was? 2.45. Right, I calculate the acceleration. I take the square root of that. Second answer, enter. And I get 0.9. 0.9. I'm going to select 0.9 as the answer. This is all, you realize this is all just about me being right.
Yeah.
And of course I'm right. I'm going to post a solution to that one to Google Classroom after we finish up here. 0.9, okay. Coefficients of static and kinetic friction, 3 kilogram block and a horizontal desktop are 0.4 and 0.3 respectively. What is the force of friction on the block when a 15 Newton horizontal push is applied to the box? Well, it's a little bit tricky here because we have to work out. When you push on it with 15 Newtons, is it going to slide or not? When you push on it with 15 newtons, is it going to slide or not? Well, how much friction force is there? The friction force is, well, how much, I'm going to calculate how much static friction force there is. The static friction force is the static coefficient of friction, which is 0.4, multiplied by the normal force, which is the mass of the box, which is 5 or 3, times the acceleration due to gravity, 9.8. So I've just calculated mu mg, and it's 11.75 newtons is the static friction. If you push on this thing with 15, it's going to slide because the static is only 11.76. If you push with 15, it's going to slide. So now I know that it's kinetic friction, right? What is the force of friction when a 15 newton is applied? It's the kinetic friction, which is 0.3 times 3 times 9.8. I've just calculated mu mg, but I've used the kinetic friction coefficient. It's 8.82. 8.8 is the answer. I know I'm going speedy here, but I've got 3 minutes left to do 3 questions. Policeman's investigating an accident, measures the skid marks left by a car. He determines that the distance between the point that the driver slammed on the brakes and the point where the car came to a stop was 28 meters. From a reference manual, he determines that the coefficient of friction between the tires and the road in the prevailing conditions was 0.3. How fast was the car going when the driver applied the brakes? Well,
So we're looking for velocity. Yeah.
so we want to find what was the initial velocity of the car as it skid to a stop. So we have the coefficient of friction, and I demonstrated in a lecture, in order to save myself time here, I demonstrated in a lecture that the acceleration of a car skidding to a stop was mu times g. So he found that the coefficient of friction is 0.3 multiplied by 9.8 is equal to, that's the acceleration. So the acceleration is 2.94, and I want to find the initial velocity. So I'm going to use v squared is equal to v naught squared plus 2a delta x. When I do that, times what's the distance, 28, equals, and then square root. When I use that kinematic equation, I get 12.8 meters per second as my answer. I guess I got to post a solution to that one as well. 22, 55 kilogram box rests on a horizontal surface. The coefficient of static friction between the box and the surface is 0.3. A horizontal 140 Newton force is applied to the box. What is the friction force on the box? It's the same. It's the same.
161.
It's the same deal because I'm going to do 0.3 times 55 times 9.8. And I'm going to get 161. So I'm going to choose 160 and see what it says. Wrong! What did I do wrong there? Well, I was rushing, first of all. 55 kilogram box, the static coefficient friction on the box and the surface is 0.3. I did 0.3 times mg.
What?
I just did mu mg and got the static friction force. This horizontal force applied to the box is irrelevant.
Oh, is it not going to move though? Because
Yeah,
you
it
need a
doesn't
big
move
force?
because in order to move it, you'd need more than 161. So what is the friction force on the box?
So is it 0?
That's weird. That's the answer, kids. Don't you wish you had this option? Because the answer is 140. Oh, I'm silly. This is, oh my gosh. I've embarrassed myself in my own meeting. The friction force that I calculated, 161, is the maximum static friction force. This thing's not moving, which means the net force acting on it is equal to 0, which means the friction force is 140 newtons because it exactly opposes the force that's being applied to it. Oh my goodness. Wow. Yeah. So the answer is 140. Oh shoot, I didn't get 100 on this, but that's okay, I guess. Maybe not. I push downward on a angle 25. Oh, trunk of the flat surface. What's the most massive trunk you'll be able to move? Wow. This requires quite a bit of solution. And now we are overtime. Does anybody have difficulty with being overtime?
No.
No? Because I don't want to get in trouble for keeping you from doing other things. Okay. Okay. 25 below the horizontal, 750. Okay. That wasn't the right color. How is that not the right? How is that not the same color? Sheesh. All right. All right. So here's the idea with this problem. I didn't do the bucket again. So I have this mass here. It's on a horizontal surface. And I'm pushing down on it with a force this way that's 25 degrees below the x-axis. So when I draw my free body diagram for this, I have the weight mg directed downward. I have a component of the push force directed downward, which is the opposite component. If this is the angle here, then it's the cosine component of the force that goes this way. And it is the friction force that goes this way. The sine component of the push force that goes this way, and the normal force that goes upward. This is my free body diagram for this situation. So how big of a crate can I move? Well, I'm pushing with F cosine theta against a friction force that is going to give me a massive crate multiplied by an acceleration. But in order to move the crate, all I have to do is I have to exert F cosine theta that's greater than the static friction force, that is mu times the normal force. So the force that I push with has to be greater than the static friction force in order to move it. So up here, what's the normal force equal to? I see here that the normal force isn't just equal to mg, but the normal force is, in fact, the normal force upward is equal to mg plus F times the sine of theta. So I have to plug that in down here as mu times mg plus F times the sine of theta. So there's the mass right there that I'm trying to solve for. What craziness is this? So on this, I'm going to write mu mg plus mu F times the sine of theta. And on this side, I've got my F cosine theta. I'm going to solve for m here. So I'm going to subtract mu F sine theta over to this side, and I'm going to divide by mu g. So my final answer is that the biggest crate, I'm going to write it up here, the biggest crate that I can move is F cosine theta minus mu F sine theta divided by mu g. Oh, that is a complicated multiple choice question. Heavens. And now I've got to switch back to my window, and I don't have the numbers to calculate. So we're going to view, see how that works out in solution view. Are the numbers randomized for you guys on this? Like, do you have different numbers?
I think
It's the same.
So your parting gift for joining the meeting today is that is 81 kilograms. And our last question. A truck carrying a 20 kilogram crate up a sloping road, the coefficient of static friction between the crate and the bed is 0.4, and the coefficient of kinetic friction is 0.3. What is the maximum angle of slope that the truck can climb at constant speed if the crate is to stay in place? This problem's actually been solved a couple of times in my lectures, but we'll go ahead and solve it again. And I go away. I want this menu to go away. Fine, be that way. All right. So this crate is on an incline. Oh, it's the worst. Look at that. It's like I'm not even trying. I miss my whiteboard. I miss being in a classroom. You know, I honestly do. I know that there's probably a lot of people who are like, yay, school is done. I don't feel that way. I wish I was back in school. So there's a component of the weight, mg sine theta, directed this way, mg sine theta. And there's the friction force up the incline, like that. And the normal force is this way. And the weight force component, mg cosine theta, is this way. So here's what's happening. Down the incline, if I'm going to do Newton's second law, the sum of all the forces is equal to the mass times the acceleration. mg times the sine of theta down the incline minus the friction force has to be equal to the mass times the acceleration. But we don't want it to accelerate. We want that acceleration to be equal to 0. We want it to stay put. So mg times the sine of theta minus mu times the normal force has to be equal to 0. Well, the normal force is equal to mg cosine theta. So mg sine theta, I'll just take this bit and add it over to the other side of the equation. mg sine theta is equal to mu mg cosine theta, because that's what the normal force is equal to. The mg's cancel, and what I get is that the sine of theta is equal to mu times the cosine of theta. Divide both sides by the cosine of theta, then the sine of theta is, well, sine of theta divided by cosine theta is equal to mu. So the tangent of theta is equal to mu, and so that angle, that critical angle that the slope can be so that the thing doesn't slide, is going to be the inverse tangent of the coefficient of friction. And as I said, that was a solution that I did a couple of times in the lecture videos. So what I have to do to find this angle is I just have to take my my calculator here and find my static friction coefficient, which is 0.4, and take the inverse tangent of that. And 21.8, so about 22, is the answer to that.